Right, well, thanks again to those that have been waiting, and welcome to those that have just joined us. Hope everybody's well. I'd like to thank you all for tuning in. My name's Mike. I'm from the Manufacturing Solutions team here at Quadra, and I'm joined by our applications engineer, Mr. Andrew Canfield, who some, if not most of you, will know already. Today, the objective for us is to raise your awareness for some new industry standard design validation tools recently acquired by Autodesk, that being Nastran in CAD. And as the name suggests, it's in CAD. You don't have to go away and learn a whole new system. Now, this new kit is driven within your inventor, so good news already from the start. We should be ready for Q&A in about 25-30 minutes time. I'll start by quickly adding some kudos points to the Nastran name, what it is and what it does. We'll explain who it's designed for and the interface, so how hard it is to drive. Then I've got a graphic on its capabilities and a very quick outline on each area. The business benefits are, as always, very important focus, so we'll be looking at the numerous angles associated with you improving the workflow in this way. We've got case study materials galore to choose from, so I've picked out a mainline custom product manufacturer from ours, which we'll go through very quickly before handing over to Andrew, who has prepared a bit of a show and tell to demonstrate Nastran and the output you would expect to see from it. Afterwards, we'll summarise on how Quadra can support as a solutions provider, finishing off with any Q&A and comments raised throughout the session. So, as I say, all in all, we should be finished in about 30-35 minutes time. On the subject of Q&A, you'll see the chat feature to the right side of the screen. You can use this to send questions or comments in at any point, again, which will form the basis of the discussions later on. And there is no such thing as a daft question, by the way. Anything that's relevant and pertinent, fire it across to us. So, Nastran, strange name. What is it? Nastran as a word was born out of NASA's structural analysis requirements and developed since the late 60s, early 70s. Nastran, as we all know, is hardly a small organisation. It has hundreds of sites, most of which have their own research teams internally, working on various craft, satellite and product designs, and assessing durability in the harsh environment scenarios associated with each. So that's temperature, vibration, heat transfer, resonant frequencies, will it bend, buckle, break, bust, and so on. As a group, NASA realised that over the years these boffins were drawing up their own calculus, but also creating basic analysis tools specific to their individual test areas. A subsequent review in '64 recommended that they all unify these modules under one generic program that would then be rolled out across the whole of NASA to verify structural analysis results. As this was NASA, naturally the project was financed and monitored closely, very closely, by US government funders, and as a final product, Nastran was born and has continued to be developed beyond just structural analysis into the well-established, industry-recognised FEA program that we see today. And by the way, FEA standing for Finite Element Analysis, will probably come up a few times during this session, for those of you not in the know. While the source code for Nastran remains intact, there are three main offshoots, those being MSC Nastran, operated by the original developers and still primarily used as a structural analysis tool. You then have NX Nastran, which is owned by Siemens as part of their PLM offering. And there at the bottom you have NEI Nastran, which is now Autodesk Nastran in CAD as of 2014. There we are. Our focus naturally is on the latter. So, Nastran in CAD. The NEI Nastran in CAD is essentially the high-end FEA solver that's used to run each of the analyses. It's proven to accurately predict the performance, optimize designs, and validate product behavior before you had to cut metal or build the prototypes. It's very versatile and scalable tool sets as well, so designers and engineers can all intuitively check their design decisions whilst they're working in Inventor, alongside QA teams and qualified analysts further up the chain. So basically, you don't need a PhD to drive it, far from it. And because not everybody uses FEA at the same time, all the time, Nastran is purely a network license, so it's a network deployment, so that access is available flexibly to any CAD workstation, depending on the number of Inventor or SolidWorks licenses you have, works with Inventor or SolidWorks alike. Who's it for? Which sectors are using it? Best way to answer that is to ask, who's it not for? It doesn't matter if you're producing a spring-loaded biro or a nuclear decommissioning arm. Your products will be validated at some stage, and there are countless research sources out there that we have access to that conclude that simulation is the most cost-effective way to validate and optimize the product performance from the earliest design stages, before it's built, not after it's installed. As engineers, your job's to make reliable products that fit the specification in the fastest, most economic way possible, both to the customer and to you as the company. And as I said earlier, Nastran enables all users to be guided through the various stages of the process, setting up the parameters and validating the designs in real time, themselves, yourselves, without slowing down the design process by contracting, for example, contracting out the analysis to external firms, or even just blissfully working away on a part where the base features are structurally doomed to fail later on. Has been known, as I'm sure a lot of you out there can empathise. Question, how hard can it be? In other words, is it hard to drive? No, absolutely not is the answer. As you'll see above, the standard ribbon is structured to be followed from left to right in such a way that it gives you a checklist of the process you need to follow to preload the right parameters. You start with the background system settings, then type the type of analysis that you're doing. You then look at the material properties, the surrounding environment, then providing that no guidance errors have been flagged up by the software at this stage, you proceed to mesh, then solve and view the results. Furthermore, and this is quite important, because you set up the first analysis in CAD, or in Inventor for example, you can then refine the design and rerun that analysis with the new refinements. So you no need to save it as something else, convert it, reopen it in other softwares, etc. What capability? What does it do? So you're in Inventor and you click on your newly acquired Autodesk Nastran ribbon tab. You'll then be able to subject your numerous components and assemblies to either basic analysis in orange and advanced analysis in blue. In the orange corner, we have normal modes, which determines the undamped natural mode shapes and frequencies of structures, which allows you to resolve problems with noise and vibration, for example. You have pre-stressed static and normal modes to analyze structures subjected to initial stress, and you can also model the effect of the initial stress state on the structure's displacements, secondary stresses and modes. You have linear static analysis there on the top right, one of the most common types. Determines stress, strain and deformation resulting from applied static loads and static constraints. Thermal stress, moving on, supports the analysis of structures under thermal loads, straightforward enough. You've got linear steady state heat transfer, which uses the principles of conduction and convection, and you can examine designs for temperature distribution across the part, models, blocks. Assembly modelling with contact. So Inventor Pro users will recognise this one. This is real-world simulation of assemblies using different contact iterations, including sliding, friction and welded contact types. You also have buckling, which could be a popular one. Assesses the stability under load and examines for sudden failure modes caused by compressive forces. And finally, in the orange side, we have composites. So it provides straightforward handling of ply data, analysis based on latest test failure indices, as well, with reliable linear and non-linear results. So non-linear being after the point of failure. Indices like PUC and LARCO2 means reliable and insightful results as well. In the blue corner, for advanced analysis, we have our responses. You have random response, which is analysis of structural behavior in response to the imposition of random dynamic loads. You have both variants of transient response. So it simulates the response of a structure through a period of time under the influence of either a constant or a time-dependent load. So impulse loading, for example. Frequency response as well there determines the structural harmonic response based upon frequency-dependent loads. You've got the drop testing, which provides realistic shock, impact and project simulation. Incidentally, the only inputs required for this one are the projectile velocity and the acceleration. There's a good example of take the pain out of sim there, particularly from the drop test side. It's very easy to use now. You have non-linear, transient and steady state transfers, heat transfers. Steady state heat transfer solves heat transfer problems with non-linear thermal boundary conditions, such as temperature dependent thermal properties, and the transient version solves heat transfers with non-linear thermal boundary conditions that vary through time. So that's that power fluctuations and the like. Last two, you've got non-linear static. So it computes advanced non-linear solutions like large displacements or rotation, plasticity, hyperelasticity, creep, and you have at the end there advanced non-linear material, which so the solver itself captures the non-linear phenomena such as again plasticity, hyperelasticity, shape memory effect as well. It enables you as engineers, designers, analysts, whatever, to model a wide range of materials from metals and shape memory alloys to rubbers and soft tissues, anything and everything really. How reliable is it? So we're looking at reliability in QDOS here. All of the capabilities that you've seen on the last slide are underpinned by NASA, an organisation that spent over 5 decades in development and rigorous testing. Nastran, it has a long, versatile history and a proven track record to deliver these real-world analysis results. For those of you who are aware of NFAMS, it's now under the Autodesk banner, and Autodesk are continually validating these results quite rigorously using NFAMS, which is a physical testing lab. They're using other published benchmarks as well, of course, and overall it provides assurance to not just Autodesk themselves but to customers that the results are reliable to real-world conditions. Not to mention, of course, there are success stories out there for customers who are using it and have got these real-world versus the virtual world results from most design-critical sectors. A couple of examples are there on the screen. But if you'd like to read a few, bit of bedtime reading, let me know in the comments and we'll get in touch with you afterwards with the information. Just like to mention as well, something that I've dropped in at the last minute. We have various access sources to academic white papers published on the simulation front. Simulation forms part of this particular Tech Clarity white paper, which focused on industrial equipment designers and manufacturers. And if you have a look at this page here, you'll see in highlighted almost 50% of the top performers in the sector, in the industry, were those most likely to be using simulation as part of their integrated design workflow. So some really interesting reading there on page 11, as you can see. Page 3 talks about simulation and it's mentioned throughout the paper as well. So if you want a copy of that Tech Clarity white paper, again, please let me know. Let's have a look at one case study in particular. Niner bikes. Each of Niner's bikes starts out with a clean sheet of paper. So this is a USP. They design every bike specific and customized to the actual recipient. So it's designed from scratch. That presents its own challenges. You've got to get the balance right, basically, between optimizing the stiffness, getting the ride comfort right, and minimizing the weight, down to the nearest gram in most cases. All this without making any compromises in the bike's strength. Every bike must then exceed the intense CEN and DIN Plus testing standards for strength and safety to ensure that they're up to tackling the demanding ride conditions in the harsh environments that they're ridden in. Nastran, because of its track record and the versatile range of analyses that fit the bill, is now used integrally from the beginning of each design stage to refine the frame stiffness and the ride specs during the in-CAD design process, whilst shaving off those precious grams of the chosen composite materials in the process. And it's important to mention as well, these are composite materials that are being simulated and analysed within Nastran as they're going along. All this without compromising the actual strength and durability of the product. The versatility of Nastran allows Niner to not only optimise the frames for stiffness to weight, but it also helps them devise new testing strategies for their R&D that current protocols don't cover. So it's basically a one-stop shop solution for all of Niner's FEA needs. Let's focus a bit on the business side of things now. Any underlying flaws in the design process earlier on can result in business costs from any number of angles. As a business strategy, simulation of any kind is proven to deliver savings and targets beyond that of just the designers in the design office, and I've laid some of the more pertinent ones out for you on the screen there. Appreciating, of course, that your first simulation project, integrating Nastran into the workflow, the first time around, it won't be the quickest. The payoff will come from project 3, maybe, say 4, where the systems are in place, you know how they work, and these new informed design decision processes are practiced and refined. The key deliverable here is to be able to make informed design choices earlier in the process.
Alright, morning everybody. Okay, this is a video recorded yesterday. Okay, so I started off there with the model inside Inventor, and you'll notice this has been modelled as a surface model. There's a couple of mounts that have been created as solid models there, and the main body of this exhaust is created as a surface. So from these environments on the ribbon here, you've got the link straight into Nastran, so you can see it's built into Inventor. And what we're doing now is assigning properties to the geometry. You've got a choice of single lines, shells, or solids. So because we've modelled this as a surface, we're going to apply a shell element to it, and there we're specifying the thickness. The materials we can pull through from Inventor. There's also a library available within Nastran of other materials if you need stuff that's not inside Inventor. And here you can see that it's pulling through the physical properties in terms of mass, elastic modulus, and the yield limit there. Okay, so once the physical properties have been assigned to the parts, we can associate the geometry that's going to be using that particular value. So there we can go and click on the model to assign those values. Now once this data has been acquired, we can use this duplicate function and use the same settings of different geometry within the model. So here we're just going to clear that particular set, and then we can reuse that data. It's useful to name them, rename the different groups, because then when we want to vary the analysis for later on, we can just select that particular group and then make the edits to it. So here within Inventor, just by hovering over the geometry, I'm just waiting there for the options to appear to be able to select that geometry that lies underneath the part that's blocking it effectively. So yeah, so just working through this model, selecting all the parts within it and assigning this value to the geometry. So after the shells have have been identified, and notice there's a couple of brackets there which are solid. And part of what we could do in Nastran is mix shell elements and solid elements together. So we've got the tube specified as a section, the exhaust as a section, and then these end caps which acts as stiffening members throughout the body. So now this is assigning the element type, so they were choosing a solid element type for the mounting brackets, and then it's just a question of clicking on the parts within the model. Okay, now we need to fix it in space. So here, I'll just pause that a second. So in this dialog box, you've got the option to control which degrees of freedom you want. So when it's fixed, it'll automatically lock everything down. If you want something that's going to be rotating, then it will just stop translation in the X, Y, and Z directions and allow it to rotate. If you have things that are sliding in a particular, then you can use these functions. So you've got some shortcut keys effectively to allow the degrees of freedom to be applied. Right. So when it comes to the mesh data, you can specify the size that you want. So when it comes to convergency studies, you can go back to here, this setting, and put in different mesh sizes to rerun the analysis and checking that you're getting convergence between different models. Now, because we have a mixture of solid elements and shell elements, we can use this weld feature effectively, referred to there as offset bonding. So we can lock the solid element to the shell element. So this offset bonding, that's something that you don't see in Inventor. It's something that's an added feature that you get within Nastran. So the workflow is fairly similar in terms of associating the geometry to what we saw when we were specifying the shell element. Right, so as the analysis runs, you get a scrolling screen here that gives you feedback, and this allows you to look at convergency rates. Now this is a video pre-recording, so it can actually do it that quickly in real time. It depends on your hardware that's in use. So now you can see the nodes that have been created in terms of the natural frequency from this vibration study. And from the displays, we can create an animation which will give you an idea of how this part responds when it's being shaken. Now the display here is being amplified by 10, but it gives you it gives you a visual feedback as to how it's how it responds. So there you can see the percentage increase in movement. You can toggle it down to actual movement if you want to see what the real world response is. So in addition to a graphical data feedback, you can also extract plots. So here I'm going to create a graph of the movement in the X, Y, and Z directions, and that will be plotted against the frequency that's been studied. So clearly that peaks out about moving over 20 millimeters. In addition to the animation displays, you can also create sectional views, and you can look inside the model and see what the values are sections. That's something that you can't do in Inventor as well. Okay, so this is the options. Once I've got this model set up, I can copy the analysis, and that's all the values of it that I've just put in. I can reuse them effectively, and I can make changes to them. So in this instance, I want to change the thickness of various parts of that model and rerun the analysis. So because I've subdivided those into sections beforehand, it's just a question of going and editing each value now. So for the end caps, I can go and make them from a thicker material. So this is, I'm coming out of Nastran now, I'm back in Inventor. I'm going to these surface mounts, just changing the thickness on these from the previous thickness. So I'm toggling from Nastran into Inventor, make the modification, then I can go back into Nastran. So from the ribbon, just pick the Nastran interface, remesh my model. And this is real time further meshing. And then rerunning the analysis. So again, once this is completed, I extract the values from the graph, as we just saw in the previous exercise, and we can see how the thickening those different parts has affected the natural frequencies of this exhaust. Because for a new product, trying to analyse the frequency response is going to be time consuming and expensive when you're trying to use road data. So this is just comparing the two results. So using the shell element is one of the advantages of being able to create a surface body. The shell element will be used less quadrilaterals and reduce the number of nodes that are needed. So that will help speed up the analysis further down the line. And being able to use the welded contacts to link the solid elements and the shell elements together. It's just a way of just generally increasing the speed at which models can be put together and analysed. There you can see the changes that those thicknesses of materials have made to the study, and there's less movement, which would be expected with them being thicker. But also, if there's particular frequencies that can cause a problem, they can be seen through this study. So here, from the analysis, we can see the responses to particular frequencies. So the next stage from here is looking at those frequencies and seeing if there's going to have a problem with fatigue in the parts that are suffering under those particular loadings. Normal modes is a natural frequency analysis. Buckling for frameworks, non-linear for if you're pushing parts beyond the yield point. And then you've also got the fatigue analysis, which I've got another video of, and then you've also got heat transfer options as well. So it's just, you can see the options there on the drop down, and the workflow is reasonably similar in that you create subcases and loads for each of the different analyses, and you enter your values into there as you need for the required analysis. Right, so once I've done this study here and found the frequencies, I then need to do the fatigue analysis. So this is using the fatigue analysis, and it's just going through here. You can see these subcases and entering the values that are needed. So there's options of what studies you need, what are the values to put in for the various subcases, and then putting in the range that's needed for the frequencies. And also you'll need to know what the SN data is for the material that you're going to be using, and that's entered as part of the fatigue data. So we'll just come to that in a second. So here we go. So this is the right-click driven. Okay, so that's all the data needed for the fatigue analysis. We can then run the analysis. Again, this is edited, and then it's just a question of going through the results, picking on the output required, and seeing what damage can be created under those load conditions. And here under this, the specify max and min, we can see that there's no particular damage being created under these conditions for this particular part. So that's obviously fatigue study is something that's very difficult to carry out in the real world. So it's something that will help speed things up and hopefully reduce costs. Okay, so that's the end of the fatigue. That's the natural frequencies for this particular model.
Fair enough.
And that's the study complete.
Thanks very much for that, Andrew. Thanks very much. Cheers for that. One question I've got immediately, I know there have been some questions raised, which we'll come to in a minute, but just on that note, you know, you skipped the analysis bit for the benefit of the webinar. Mm-hmm. What sort of system requirements would you sort of suggest, and what would we need to look at specifically in order to drive this, if it like fluidly?
Better the PC, the quicker it will respond, but generally an inventor capable PC will run Nastran. It is quite memory and disk space intensive, so once it is calculating sort of hundreds of thousands of points on the meshes and the nodes,
yeah,
and these analysis need saving. So if it is a large model, you are going to be creating a lot of data. So the bigger the disk drive you've got might help.
Right, okay. That's cache it. Yeah, okay. No, thanks for that. I don't know if somebody else has asked that. We'll come to it, and I apologise if I've read out somebody's question already. Right, so turn back to the slides just now. Not long to go, I promise you. We'll just have a look at how Quadra can help. Obviously, as you've seen, we have Andrew and the team here at Quadra, and as you probably appreciate, like all software, you get the best out of it with the right foundations in place. So this is where the expertise of the guys here comes in. If you looking at this, if you find that Nastran might have a part to play in the workflow, it certainly has impact across most, if not all, sectors, so it will affect you in some way, shape or form. We'd love to get involved to help you realise that potential. Typical scenario, those who've dealt with Quadra before from a consultancy angle know that we need to really ideally sit in front of you and find out which sim areas Nastran has that will have a fit, and see what requirement needs to be, what your requirements are and what objectives need to be achieved. In terms of the actual offerings, we've got bespoke training courses. You can't really run a scheduled training course on Nastran because it's that vast. You typically might not need all the bells and whistles at all the time, so we'd suggest a bespoke training on the areas that you need to focus on. And as part of the Autodesk Developer Network generally, we're in tune with sort of regular updates, best practice, and so on, which we can help you with as we go on as a partnership on a Nastran project. So let's have a look at some of the questions that have been raised so far. I've raised the technical specifications one, so somebody's jumped in already. Apologies. We've got a question here. Andrew, first off, what's the difference between, because we've talked about Nastran in CAD, and there's also Nastran, Autodesk Nastran on its own. Is there any notable differences between the two without the in-CAD?
The benefit that you have of in-CAD, like you can see from my example there, if you want to make a modification to the geometry, you can switch out of Nastran straight into Inventor, make the modification.
Yeah.
And then so you can work between the two environments smoothly. Nastran on its own is you'd import the geometry into it and then you run the analysis.
Right. Okay. And just as well, in terms of the licensing, because I mentioned before in the presentation, everyone, that it's Nastran in CAD is a network license only, if you will, so it can be shared between multiple seats. But do you know at what point it borrows the license from the server? Because you've got the Nastran tab in there. When you click on that tab and you bring the environment, it then takes that license from the server.
I typically would keep it until the Inventor's shut down.
Right.
So if you close it and then it gets returned to the...
Right, so you borrow it and it takes a license from Nastran, and then when you close Inventor, it then sends it back to the server. Yeah. Right, okay. That's useful to know. Version requirements on Inventor. Sorry, I'll read the question. What are the version requirements on Inventor to be able to use Nastran in CAD?
Right, it'll be year for year. So if you have 2015 Inventor, you'll need 2015 Nastran. If you go for 2016 Inventor, you'll need 2016 Nastran.
Right, so the two need to be aligned. The two versions need to be aligned up. Right, okay, just for that. Question here looking through, is there a 32-bit available for download?
No, it's all 64-bit.
It's all 64-bit. Okay, this is not really releasing 32-bit then. There's a couple more questions on here, but I think they're sort of relating directly to individual workflows. They're getting a little bit technical other than that, I think. Having a look at this, what we'll do for those questions, appreciating that some of these look like they're going to be quite long answers that might not be relevant to everybody, so we'll respond to those later on. At any point, by the way, if you want any of these slides or information from Andrew as to how Nastran could affect sort of your products directly, indirectly, get in touch, send me an email, put our details on the display for the time being. That's pretty much it, I think. The vibration testing there are test cases for any manner of areas for simulation that we can look through and discuss with you. So get in touch, give us a ring, send us an email. We're happy to pick things up. Thanks for joining us today. Hope you found it insightful, and we will hopefully speak to you soon. Cheers for now.
Yeah, thank you.